Okay, this is our flipped classroom for section 5.5 in calculus, the trapezoid rule. What you're going to need for this is the PDF of the lesson, which is on the web page. You're going to watch Greg Kelly's PowerPoint, and part of the PowerPoint deals with Simpson's rule, which is in your textbook, but it is not an AP topic, so disregard Simpson's rule for section 5.5. And you need to view the Khan Academy video. There's the link, which you can get off this script, or you can also get it on the interactive topic sheet. So we got Mandeep here to help us get through this, so I'm not talking to myself. And what we're trying to understand is that maybe this puzzled you at the time, maybe not, but in section 5.5, when we were dealing, or section 5.1, when we were dealing with LRAM and RRAM, the mean of those two was not equal to MRAM. And that's something that, maybe you noticed that and were troubled by it. The mean of LRAM and RRAM is equal to something. It's not this. What is it and why? Okay? So, here's an example from when we did this problem in 5.1, where this function, x squared plus 1, the program generated these values, but that, the mid-RAM value is not halfway between RRAM and LRAM. Okay? So, we're going to go over two examples, 1 and 2, and you're going to do two exercises, 3 and 7. Example 1 is a continuous function, and you're going to contrast the example 1 in your textbook with the function that Sal Khan uses in his video, and you want to contrast this, whether one of ours is overestimated, the other one's underestimated, and how come that's true. Example 2 is ordered pairs, although it is a continuous function, and then you're going to take that and try to do exercise 7. Okay? Now, as we begin, problem 33 is the objective question we want you to try and answer before you begin. So here's the question, here are the choices, and then this answer, which we're not going to go over in the video, is on the PDF at the end. And you can compare the solution to this to what you anticipated the solution would be. This is problem 33 at the end of the section. So you may want to take a moment now to pause the video, whether you can read it off here or not. In your textbook, you go to problem 33 at the end of section 5.5, read the question, give some thought to it, and then we'll come back to this question. You're going to come back to it at the end of the lesson. So we're going to pause the video for just a moment. Okay, so you were considering the problem, the multiple choice question at the end. And now we're going to go through the derivation of the trapezoidal approximation. Here's the area of a trapezoid, which is 1/2 the sum of the two bases, so you're getting the average of their sum, times how tall this is. And that's something you did beginning in geometry. And if we apply that to what's going on here, the height of this trapezoid, if we picture this being turned on its side, is delta x. So if we move this h to the front here and call this delta x, now we've got this expansion where these are the lengths of the bases. And those lengths of the bases, since we turned it on its side, are actually going to be the dependent values of the graph. So we could look at it this way. That's the height times the first trapezoid. The first trapezoid has this endpoint, this dependent endpoint, dependent value of A is the endpoint, and the first subinterval. This is the area of a trapezoid times how tall it is. Plus, this is our second trapezoid, plus so on. The leftmost endpoint and the rightmost endpoint trapezoid are only going to represent one edge. All the interior dependent values are going to be shared by two trapezoids. So if we look at that, we just take this and paste it here. We could think of it as, again, we factor out this 1/2 now, and say what I've got, h over 2 times what? This f of a occurs once. But this f of x sub 1 is happening, that's the right-hand endpoint of the first trapezoid, and it's the left-hand endpoint of the second trapezoid. So after I factor the 1/2 out of that, I combine my like terms, I'm going to count all of the inner edges, which are shared by two trapezoids. I'm going to count them twice. The only edges of the trapezoid that can't count at once are the leftmost endpoint and the rightmost endpoint. And you're going to see that what happens is that the trapezoidal approximation is going to exactly correspond to the average of the LRAM and RRAM from section 5.1. So we're going to go to your textbook, an example 1 on page 307, and you're trying to follow what's happening here in example 1, which is the curve is x squared, and you're estimating the area of the curve between 1 and 2 with 4 approximations. So you're going to follow what's on page 307 of your book. I'm not going to repeat it on here. Follow what's on page 307 of your book. Try and contrast that with the curve that Sal Khan picked on the video. And then after you have a moment to go over that, go to exercise 3. And then when you restart the video, we're going to go over the solution to exercise 3. That's what I should have done. Okay, so exercise 3 is the same problem as example 1, except instead of x squared, it's x cubed. There's still 4 partitions, except that we move we're integrating it from 0 to 2. So the height of each trapezoid, when you turn it on its side, is going to be the distance from 0 to 2 divided by 4 subintervals, which was given. So the height of each trapezoid is 1/2. So if we take the 1/2, and then we put that as our delta x, and we also have this 1/2 because that's the average of the two bases of the trapezoid, we put on our dependent values. Our dependent values are 0, where we're beginning, 2, where we're ending, and every 1/2 in between. 0, 1/2, 1, 3/2. The function is cubing the inputs. And then we're counting the interior points twice, because they're shared by two trapezoids. So if you simplify the arithmetic, you're going to end up with 17/4, which is 4 25/100. If we then go to the areas program, the folder that we gave you, trapezoids is one of the options. So if you click on that and you type in x cubed is your function, which corresponds to problem 3, and you have to give it the domain, which we're telling us we're evaluating between 0 and 2. N is the number of subintervals, which is 4. You have to come up with the y values. So just coming up with y values so that the program will draw the graph. And there's the picture. The output is telling you the same thing that we calculated, 4 25/100. The actual exact area of this curve between 0 and 2, under the curve, is 4. So we overestimated the area of the curve. And how does that compare to what happened on the Khan Academy video? If we go back to the RAM program from section 5.1, that's spitting out LRAM, RRAM for the same function. The mean of those two outputs is what we got for the trapezoid approximation, which does not match up to MRAM. So we're going to move on to one more example, example 2, and ask you to do one more problem. So example 2 is on page 308, and it's about temperatures. And they're asking for the mean temperatures from over the course of 12 hours. And the idea is, well, you could just add up those numbers and divide by 12. But if instead we did that, and we took the area under that, under plotting those temperatures, that would give us a better idea. And why is that? Give some thought to that. If I'm on page 308, you follow this. You're just taking the mean of what's going on, the mean of the area under those temperatures. And then you're going to pause the video while you go through example 2, and then we're going to come back and go over exercise 7 with you. So exercise 7 is same as the example with different numbers. What I want the average from A to B of what? Of the area under this curve. So you were given these points. So if I think of this in terms of constructing trapezoids, I would have this. My delta x in this case, as I'm changing here, is 1. So I have 1 times 1/2. I count the first endpoint once. I count the interior endpoints twice. And I count the last endpoint once. You end up with 74. That would be the approximate area by the trapezoid rule if we, that's the total area. The average of that is 12 1/3. So the last thing is to come back to the standardized question. So here's the work for problem 33. And then when we get to class, you're going to work collaboratively on the other assignments, and we'll take it from there.